22. A given coin has a mass of 3 gram. Calculate the nuclear energy that would be required to separate all the neutrons and protons from each other. For simplicity, assume that the coin is entirely made of copper 2963 atoms of mass 62.92960 atomic mass unit. Also given mass of the proton 1.007825 atomic mass unit, and mass of the neutron is 1.008665 atomic mass unit. So 22nd, here a coin of mass m is 3.0 gram. It is made of copper Cu 2963, and mass of that is given as 62.92960 atomic mass unit. The mass of the proton is given at 1.007. हार्ड कॉपी जरूर रखें, जैसे मुझे देखने की जरूरत पड़ रही है, आप भी उसको साथ साथ देखें, तो हार्ड कॉपी जरूर अपने साथ रखनी है. 825 atomic mass unit, and mass of the neutron is 1.008665 atomic mass unit. So we need to find out the total energy given to these so that the neutrons and protons can be splitted, means they can be detached. That means ultimately we have to find the binding energy which is binding these nucleons within the nucleus, and that is equal to mass defect into 931 mega electron volt. Here this is total mass defect of all the atoms in this. So first of all we will find out the number of atoms in this 3 gram of copper, and then we will find the mass defect in one atom multiplied by the total number of atoms, that will be equal to the total mass defect, and then we will multiply by 31 and you will get the exact energy. So first of all, the number of atoms in the copper that coin, that is equals to 3 into Avogadro number 6.023 into 10 raised to the power 23 divided by 63. This 6 and 63 almost 1/10 is there, but it will be less than 3. So that comes to be 0.2868 into 10 raised to the power 23 atoms. So the mass defect in one atom will be equal to delta M equals to 29 into mass of the proton plus 34 into mass of the neutron minus mass of the atom, copper atom. So that comes to be 29 into 1.007, this one 825 into 34 into 1.008665 minus this M is 62.92960. So this 29 into this multiply, that comes to be 29.22707 plus this comes to be 34 into this comes to be 34.29478 minus 62.92960. After adding these two, we get 8 and 7 5, 7 and 8 and 7 5 and 15 5, then 7 plus 1 8, then 7 plus 4 11, then 9 to 11 and 12, then 9 to 11 12, and then this will be 2 plus 2 4 5, and this is 63. So this comes to be 63 5218. This 2 will be twice नहीं होगा. 7 plus 8 2 4 5, So 7 plus 8, 5. Then 7, when we add these two, we'll see 7 plus 8, 15, 5, remainder is 1. Then 1 plus 7 is 8. Then 7 plus 4 is 11. Then 2 plus 9 is 11 and remainder is there. So 12. And 2 plus 4, then this becomes 5. And 9, 4, 3. And 3 to 5, 6. So it comes 63.52185 minus 62.92960. That comes to be 5 minus 0 is 5. Then 8 minus 6 is 2. Then it is 1 and they are 9. So it will become 11 minus 9 is 2. Then here it is again 1. Then this 2. So 11 minus 2 is 9. Now it has become 4. So you take one remainder here. So it has become 14. And minus 9 is 5. And then we will 2 and 2. And then this will be 0. So this is 0.59225 atomic mass unit. So the total mass defect in this many atoms will be equals to 0.59225 into 0.2868 into 10 to the power 23, and that comes to be 0.1698 into 10 to the power 23 atomic mass unit. Now we'll have the binding energy will be equals to this delta M into 931. So that comes to be 0.1698 into 10 to the power 23 into 931, and that comes out to be 158.1 into 10 to the power 23. That we can write 158.1 into 10 to the power 23 mega electron volt. So this can to be written as 1.58 into 10 to the power 25 mega electron volt. So this much energy is to be supplied to detach them from each other in the nucleus. So that is the binding energy which is binding these nucleons within the nucleus is 1.58 into 10 to the power 25 mega electron volt. Question number 23. Charges plus Q and minus Q are placed at the points A and B respectively, which are at a distance 2 capital L apart. C is the midpoint between A and B. What is the work done in moving a charge plus Q along the semicircle CRD? So here we have two charges plus Q and minus Q at A and B. These are 2L apart. So here it is C, which is midway. So this will be L, this will be L, and a D point is there. This is a semicircle CRD. So this is also L. So we have to find the work done in transferring a charge Q along the path CRD. We know that the work done is equals to charge into potential difference. The work done is independent of the path. It is only depending on the two positions where the potential difference will be there. So it only depends on the position D and C. So that means this will be Q into VC minus VD. So as far as this VC is, VC will be KQ by L due to this, minus kq by L, which is 0, and Vd will be equals to potential difference, potential due to this A and potential due to B. So that is kq upon 3L minus kq by L, that is kq minus 3kq, that is minus 2kq upon 3L. So the work done will be equals to q into 0 minus 2kq upon 3L, that is equals to 2k q capital Q upon 3L, replacing the value of k, that is 1 upon 4 pi epsilon naught q capital Q upon L. So this cancelled, so we get 1 upon 6 pi epsilon naught q capital Q by L. So the work done is 1 by yani q capital Q upon 6 pi epsilon naught L. So this is the answer. Twenty-fourth, the total energy of an electron in the first excited state of the hydrogen atom is about minus 3.4 eV, electronic volt. Then A, what is the kinetic energy of the electron in this state? B, what is the potential energy of the electron in this state? C, which of the answers ever would change if the choice of the zero of potential energy is changed? The total energy of an electron in nth orbit is given by minus 13.6 upon n square electron volt. For the first excited state, the total energy of electron for first excited state, that means n equals to 2, is minus 13.6 divided by 4, that is 3.4 electronic volt negative. As we know, total energy is equals to kinetic energy plus potential energy. Also, the kinetic energy is minus half of the potential energy. Therefore, total energy will be equal to minus half U plus U, that is plus half of the U. So here it is 3.4 equals to half of the U. That means potential energy U will be minus 6.8 electronic volt, and kinetic energy is minus half of the U, that is minus half of minus 6.8, that is 3.4 electronic volt positive. So the answer A part, what is the kinetic energy of the electron in this state? So kinetic energy of the electron in this state is 3.4 electron volt. And B, what is the potential energy of the electron in this state? So potential energy of the electron in this state is minus 6.8 electronic volt. And the C part is if the choice of zero potential energy is changed, then only potential energy and the total energy will change, but the kinetic energy will remain always same. So kinetic energy doesn't change, potential energy and total energy changes. or will change.